So last time we talked about branch and bound, backtracking and branch and bound, and we used the 0-1 knapsack problem to explain these algorithmic techniques. Today we are going to go through a numerical example that shows how the different pruning techniques can be used in branch and bound, in particular, or the different upper bound computation algorithms can be used in branch and bound. Okay? Any question? So this is the example that we will be using today. So this example has 5 items. Last time we showed an example with 3 items. That example was good for showing brute force, because when you have 3 items, brute force is 2 power 3, which is 8. So we could fit those on the board. But now with this example with 5 items, now the total number of solutions is going to be 2 power 5, which is what? 32. So that's not going to fit. So in today's lecture, we're not going to show the complete tree, because the whole point is to show how the tree gets pruned, how we can use different upper bound techniques to prune the tree and avoid exploring the entire decision tree and avoid reaching the leaves as much as possible. So let's try to review the concepts. So brute force is enumerating all possible solutions. Now backtracking, what do we mean by backtracking? How did we define backtracking last time? Yes?
We go on using the brute force, but we prune the possibilities that are not feasible.
Yes, exactly. As soon as we reach, so this is the root, as soon as we reach infeasibility at a given node, as soon as we determine it's infeasible, we just don't continue any further. So we backtrack, consider other options, and that effectively prunes the whole subtree below that node. So it's like a whole subtree below this node that we are not exploring, and this is a lot of saving in the computation. This is something that you will be implementing in assignment number 4, and you will get to experience, how much difference, these prunings will make in terms of the actual time needed to solve a given problem. So now, what do we mean by infeasible? What do we mean by infeasible? Yeah. Yes. The sum of weights of taken items exceeds the capacity. So if we exceed the capacity at this node, everything below it is going to be infeasible. So we shouldn't waste time exploring the subtree below this node. So we know that all the leaves below this node are going to be infeasible. So this is simple. The backtracking is simple. Return as soon as you detect infeasibility. Now, branch and bound. How would you describe branch and bound in general? Without referring to any specific problem or any specific bound. How would you describe branch and bound in general? The idea of branch and bound. Without referring to any specific problem and without referring to any specific bound.
Every time we are deciding, we keep track of the best solution, and then...
Okay, so we always keep track of the best solution so far, but that's not branch and bound.
But then if we check that if after a decided value, like if we selected a node, decided that we are going to take this node, and then for this tree after below that node, if it's giving less than the best value we have got so far, then we won't be using that subtree.
Okay, so how do we know that it will give less than the best value? How do we know that?
Calculating the bound?
Yeah, we calculate a bound, exactly. So this is the key idea. Branch and bound in general, without referring to 0-1 knapsack and without referring to any specific bounds. The idea is this is our root, no decision has been made, and this is some node in the tree. When we reach this node, we have made some decisions. So we have constructed a partial solution by making some decisions, but we have a partial solution. There are more decisions yet to be made. So if we can compute a bound on the best solution that we can ever reach below this node, based on the decisions that we have made. So if we can use the decisions that we have made to compute a bound on the value of the best solution or any solution that may be found below this node, and we can argue that this upper bound on the value of the best solution is going to be less than or equal to the best solution found so far. Best is the best solution found so far. So if we can somehow argue that any solution below this node will have a value that will not exceed the best solution that we have found so far, then this will prove that there is no need to explore this entire subtree, and we can just backtrack and consider other decisions, and we can prune this subtree away. This is the idea of branch and bound in general. Now, what kind of optimization problems am I implying here? So there are two kinds of optimization problems. There are maximization and minimization, right? So for maximization problem, you compute an upper bound and you argue that it's going to be less than or equal to the best solution found so far. But when we are solving a minimization problem, we will need to compute a lower bound. Yeah. So if you are trying to solve a minimization problem, you compute a lower bound and you prune if this lower bound is greater than or equal to the best solution found so far. Okay, just a note, because later this semester we may solve minimization problems using branch and bound. But the 0-1 knapsack is a maximization problem. Now, what are these upper bounds? Last time, for this specific problem, the 0-1 knapsack problem, we talked about 3 different kinds of upper bounds. 3 different ways of computing upper bounds. Upper bound 1, which was what? What was the first upper bound? The simplest and easiest and but least effective. What was that upper bound? So that upper bound, the first upper bound that we talked about last time, was simply assume that you will be able to take all the remaining items. So if this is the root node, you are at this node, there are decided items and undecided items. Just upper bound number 1, assume that you can take all the undecided items. Just assume that you can take all undecided items. Now, let's see how we can compute this upper bound for this tree. So this is the root node, node 0. And let's assume that we made a decision to take item number 1, and we are now at node 1. Now at node 1, at node number 1, we have taken item 1. So the decided items are item number 1. And the undecided items are items 2 through 5. Through 5. So now, in this case, let's upper bound 1, or at node 1, or N1, upper bound 1 equals value 1, the value of the first item, because we have decided to take it, plus sum of values of items, V2 plus V3, or let's write it in the form of a summation. Summation of VI, I equals 2 to 5 in this case. The sum of the remaining items. So this upper bound just says I can take all remaining items. So here, so this is going to be the value 21 plus the sum of values of remaining items. Well, it's going to give you the total sum, right? In this case, it's going to give you the total sum of values. So this upper bound is too optimistic. So it's going to give you the sum of the remaining items, and this is going to be 73, I think, and this will give you 94. So this upper bound is the upper bound that you compute using upper bound number 1. Okay. Now this is a naive upper bound because you simply naive or too optimistic. Too optimistic because you simply, without doing any careful analysis, you assume that you can take all the remaining items. Okay. Well, now the good thing about this upper bound is that you can compute it with only O of 1 computation at each node. How can we compute this upper bound with O of 1 computation at each node? So now we are reviewing what we discussed last time. How can we compute this upper bound? Because it looks like there is a summation here. So with this summation, it looks like this is an O of n. We need O of n to calculate this upper bound. But there is a simple way of computing this upper bound by only spending O of 1 time at each node. How? Yes?
Add them all up at the beginning and pass that value and then subtract from them the value of taken.
The value taken or not taken? So what do we subtract?
The value of not taken.
Not taken, yeah. Because this upper bound, what this upper bound says, okay, assume that you can take all the items except the ones that you have already decided not to take. So assume that your loss is limited to the items that you have decided not to take. Everything else, the ones that you decided to take and the ones that you have not decided yet, assume that you will take them all. And that will give you an upper bound. Yeah. Yes?
But if you're doing O of 1 at each node, isn't that just O of n?
No, but you will not do but you will do the summation. So you will calculate, in this example, you will calculate the 94 up front only once, not at each node. In the very beginning, right, we can sum these values only once. So this is not something that we have to do at each node. But now, as we go through the tree, for example, now, the untaken items here, we haven't decided to untake anything. But if we decide, for example, to do this, don't take item 2. Now, don't take item 2. What's the sum of taken items and remaining items? It's everything except the value of item number 2. So if you keep track of the sum of untaken items, let's call it U or UT. Untaken is initially 0. Untaken here is 0. Untaken here is the value of item 2, which is 30. Untaken is 30, which means that upper bound 1 here equals 94 minus 30. 94 minus 30, which is 64. This is your upper bound number 1. Okay? And here, so let's put the upper bound here then. And here, upper bound 1 equals 94. So basically, upper bound 1, you decrement it by the value of untaken items. As you go, whenever you decide to not to take an item, you just subtract it from the sum that you keep track of. Okay, so this is upper bound 1. Now, what about upper bound 2? Upper bound 2, well, assume that you can take every item that fits. So just check each item if it fits or doesn't fit, and assume that you can take it. So at node 1 and 1, upper bound 2 equals, of course, the value 1 plus, now now we have to selectively check each item whether it fits or doesn't fit. That will depend on the remaining capacity. So let's here put the remaining capacity, CR, remaining capacity. CR is remaining capacity. The remaining capacity here, what's the remaining capacity at node 1? What do we subtract? So the capacity is 19. We subtract 19 minus 3, which is 16. So this is going to be sum of values of all items with weight less than or equal to 16. The sum of values of all items whose weight is less than or equal to 16. And in this case, this is going to take just all items, right? So in this case, it's going to give us the same value. V1, which is 21, plus all of them are going to fit, so it's going to give you 94 again. So the upper bound here, upper bound 1 is 94, and upper bound 2 is also 94. Okay.
73.
Now, I'm sorry?
73.
70, oh, 73. Yeah, same thing. Okay, now, if we go to this node, node number 2, at node number 2, what will be the remaining capacity? The remaining capacity would be, you subtract 6 more, so you will get 10. So at node number 2, will there be a difference between upper bound 1 and upper bound 2? So you just go through the remaining items and check if they fit in the remaining capacity or not. If they fit, you take them. If they don't fit, you don't take them. So at this node, will there be a difference?
Yes. I don't think so.
No, there will be no difference because this fits. 6 is less than or equal 10, fits. 5 is less than or equal 10, fits. 10 is less than or equal 10, it fits. 8 is less than or equal 10, it fits. So we are only checking each item individually at this point. So these lower bounds are simple lower bounds. Later on in this lecture, we will cover the fractional knapsack-based lower bound, upper bound, which will be, more. It will give more accurate results. So in fact, at node N2, UB2 equals UB1. Because the weights of all remaining items are less than or equal the remaining capacity of 10. But now if we look at node 3, now the remaining capacity, okay, so this is taken, sorry, I'm implying that we are taking items. So the remaining capacity is what? So we subtract now 5 more, right? So we subtract 5 more from 10. Now the remaining capacity is 5. Now we will see a difference between upper bound 1 and upper bound 2. In fact, here upper bound 1 equals upper bound 2. There will still be 94. So here, let's write it down. UB1 equals UB2 equals 94. Okay, and here UB1 equals 64. So now at node N3, UB1 equals just, it's not going to change because we keep taking items. So it's going to be now V1 plus V2 plus V3. So these are the taken items. So let me put it in a clearer way. Sum of taken items plus sum of undecided. So the sum of taken items is V1 plus V2 plus V3. We have decided to take these. And the sum of undecided is going to be V4 plus V5. And this is going to give us 94, we know. It's going to give us the sum of all items. But now UB2 is going to be equal to sum of taken items plus sum of undecided that fit. So undecided but fits. And this is going to be V1 plus V2 plus V3 plus, now which one of the remaining items will fit? Will this fit? No. So this is a no. And this is also a no, because we have a remaining capacity of 5. So at this node, this deep in the tree, we're seeing a significant difference between the upper bound 1 and upper bound 2. So upper bound 1 is going to be 0. And the sum of the first 3 items is going to be 51, 56, 66. 66. Okay, so now at this node, now we have a difference. UB1 equals 94. UB2 equals 66. Okay, so I think this here, upper bound 1 equals 64. What will upper bound 2 be in this case? So what's the remaining capacity here?
16.
The remaining capacity here is, yes, it's 16. So definitely upper bound 2 is going to be equal to upper bound 1, because all the remaining items will fit in the remaining capacity. So this is upper bound 2. So these are very simple upper bounds. In fact, you will implement them in assignment 4. They will give you much better results than brute force. So when you implement these upper bounds, you will get much better results than brute force, but it will not be as good as the third upper bound that we talked about last time and will explain today more thoroughly, which is the fractional knapsack-based upper bound. Okay, so the fractional knapsack-based upper bound, we talked about it last time. Today we will explain it more thoroughly, and we'll go through these numbers here. We'll apply it to this example, and we'll show the numbers, the actual numbers. Any question on what we have calculated so far? Yes.
So the brute force approach is just to go through the entire tree and just find the biggest.
Yeah. Yes. Exactly. So brute force, you go through the entire tree. You do not calculate any upper bounds, and you do not even check if you have reached infeasibility or not at an internal node. You wait until you get to a leaf node, and then you check feasibility. Then you compare it with the best solution found so far. So that's why it's brute force. It doesn't do anything intelligent. Okay. Now these are simple lower bounds, upper bounds. We have seen that upper bound 1 can be computed in O of 1 time at each node. But upper bound 2, we cannot compute it in O of 1 time. At least, as it looks on the surface, to compute upper bound 2, unless you use some special data structures to keep track of what fits and what doesn't fit, upper bound 2 requires going through the undecided items and checking each one of them one at a time and deciding whether it fits or it doesn't fit. If it fits, you add it to the sum. If it doesn't fit, you skip it, and so forth. So you have to go through the remaining items. So upper bound 2 is going to be O of n. This is going to be O of 1. Okay? Upper bound 1 is O of 1. Upper bound 2 is O of n. Yeah. Question?
Yeah. When does upper bound 1 terminate early? I still don't really understand that.
Oh, when does upper bound 1 terminate early?
Yeah. When will it stop going down the tree? Because if it can take all undecided items.
Yeah, it will take all undecided items. So what will make upper bound 1 smaller? What makes it smaller? When does it get smaller? Like in this case, here we have a 64. So even upper bound 1 is 64. So 64 is a small upper bound that can be used for pruning. We will see in a minute that we can easily calculate a solution that is better than 64. So when we reach 64, we can prune. We will calculate this in a minute. But here it's 64. And if you decide, if you decide not to take another item, item 3, then this will get even smaller. Because upper bound 1, you just keep subtracting the items that you have decided not to take. So here you have to subtract 15. So you subtract 15, and it's going to get small. So upper bound 1 will still make a significant difference relative to brute force. Because at some point, when you decide not to take items, at some point, even if you take all the remaining items, you're not going to beat the best solution found so far. Right. So here at this node, so let's call it, this is node 4, and this is node 5. So here, upper bound 1 equals 64 minus 15, which is 40. 49. Okay. So now let's look into upper bound 3, which is upper bound 3 means look at the remaining items and solve the problem, solve the subproblem of the problem of deciding which of the remaining items will be taken. Solve that as a fractional knapsack problem with the remaining items and the remaining capacity. So it basically can be described as solve a fractional knapsack problem using the undecided items and the remaining capacity. Okay? Now, since we are done with these, I'm going to erase these. Now, the idea of using the fractional knapsack is just something that that we can apply to many problems, many different problems. The idea is that we have two related problems. one of them is more constrained than the other. 0-1 knapsack is more constrained than the fractional knapsack. With fractional knapsack, you have less constraints. Okay? And with the 0-1 knapsack problem, you have more constraints. So the idea is, if you relax some of the constraints and solve the problem as a fractional knapsack problem, you will get an upper bound on what you can get if you solve the problem as an actual 0-1 knapsack problem. Because by relaxing the constraints, you will get a solution that is potentially better than what you will get with the 0-1 knapsack problem, the more constrained problem. So the key idea here is that an optimal solution to a less constrained or relaxed problem gives, well, it has to be a maximization problem. Relaxed maximization problem gives an upper bound on the optimal solution to the more constrained problem. Of course, usually the less constrained problem is easier to solve. So that's why we use this technique, because we're trying to compute a bound, and we would like the bound computation to be much faster and much easier than solving the actual 0-1 knapsack problem. So we are looking at the relaxation of the problem, which is the fractional knapsack. It's a less constrained form of the problem, and it's much easier, is much easier to solve using a greedy algorithm. We use that to compute an upper bound on the solution to the problem, the original problem that we are trying to solve, which is the 0-1 knapsack. Now, in the beginning, let's first compute the fractional knapsack for the entire problem. Let's do fractional knapsack for the entire problem. So in this case, we apply the fractional knapsack. Now we note that the items are already ordered in value per unit weight. So item 1 is the most valuable item, then item 2, then item 3. So if they weren't sorted, you would have to sort them in order to be able to apply the fractional knapsack to them, so that you don't have to sort them each time. So you sort them only once in the beginning, and then you don't have to sort them at each node. It would be terribly inefficient to sort the items at each node in the tree. So you will be sorting them an exponential number of times. So there's no point in doing that. We sort them only once in the beginning. So in this case, for the fractional knapsack, so we will take item 1, with weight 3 and value 7. Then we'll take item 2 with weight 6. No, not 7, 21. Sorry. I put the wrong number. Item 2 with weight 6 and value 30. Then we take item 3 with weight 5 and value 15. When should I stop? So how much weight? What's the sum of weights so far? 9 plus 5 is 14, and the capacity is 19. So I have 5 more. I can take 5 more. Now, can I take item 4 entirely? No, I will take half of it. I will take 4 kilograms of item 4. 5 kilograms, sorry. 5 kilograms of item 4. And this is going to be 5 with a value of, what would be the value? 10, yes. So now what's the value that I have taken here?
76.
What's that?
76.
76, yeah. Now this 76 is an upper bound at this point. So I know now, because I solved the less constrained problem, the relaxed problem, which is the fractional knapsack. So I did not honor the integrality constraint, and I took fractions. I got 76. Now this is an upper bound because if I solve it as a 0-1 knapsack problem, I will get something that is less than or equal to 76. I cannot beat this with if I solve it as a 0-1 knapsack. In fact, most likely I'm going to get something less than 76. Okay, and the solution indeed is less than 76 in this case. So this is an upper bound. But now using this greedy algorithm, can you think of a way of computing a lower bound on the value of the solution on the value of the optimal solution to the 0-1 knapsack problem using the same method?
Just do it in reverse. Sort the items in reverse from a lower bound.
Okay, well, in fact, okay, so this is, okay, we can do this. In fact, we can say that 0 is a lower bound. So you can always say that 0 is a valid lower bound, but we are interested in the largest possible lower bound. So, there are valid lower bounds and there are useful lower bounds. Not all valid lower bounds are useful. A lower bound, the larger, the more useful. The larger, the better. For an upper bound, the smaller, the better, the tighter. So an upper bound is tighter when it's smaller. A lower bound is tighter when it's larger. So we are interested in a reasonably large lower bound. Yes?
Couldn't you just do the same thing but not take the last value?
Exactly. That's the idea. If I just don't take the last value, this is going to give me a lower bound. And why is it a lower bound? Why is it a valid lower bound?
Because it is taking the entire items. Like this, then till that point, all the items were taken in full amount.
Yes. Because this is a feasible solution that honors the constraints of the 0-1 knapsack problem. So this is a feasible solution, a valid solution, and by definition, the optimal solution will have a value that is greater than or equal to the value of any feasible solution. So the value of any feasible solution is a lower bound on the value of the optimal solution. Okay. So basically, any feasible solution that you find will be a lower bound on the value of the optimal solution, and the larger that the value of that feasible solution is, the more useful it will be. So this will give us a lower bound of 66. Now, in fact, this 66 gives us a lower bound, but it gives us an initial feasible solution. So now this solution, items 1, 2, and 3, this is a feasible solution. And we can think of this as the best solution found so far, even before we start traversing the tree. Before we start traversing the tree, we already have this solution as the best solution found so far, because this is a valid solution. So this is feasible. And you can think of it, initially, this is the best solution found so far. Now, what does this mean? Now, if you look at, knowing that you have this solution and it's feasible, this will allow you to do some pruning using some of these bounds. It will allow you to do pruning, for example, here. If you get here, with an upper bound of 64. So 64 is already below this feasible solution that you already have. So I already have a solution with 66. I'm not interested in something with an upper bound of 64. So given this feasible solution, I can prune based on this upper bound. Okay. So now still we haven't seen how to use the fractional knapsack to do the upper bound computation during the enumeration, during the search. So far, all what we have done is computing an upper bound and a lower bound before we start this search. We haven't started the search yet. Now, during the search, let's calculate these an upper bound upper bound 3, let's say at node 1. At node 1, upper bound 3 will be equal to the value of the item, value of item 1, because we have decided to take it, plus fractional of the remaining items and the remaining capacity. So remaining items are going to be V2, V3, V4, okay, V5, and the remaining capacity, which is 16. Okay, so we are assuming here that we have a routine that is called fractional. It solves the fractional knapsack problem. Here we are given it the remaining items or the undecided items, V2, V3, V4, V5, and we are given it the capacity, which is the remaining capacity of 16, and then it will compute that. It will solve the fractional knapsack problem for the remaining items, and it will add it to V1 because we have already decided to take V1. So this is going to give us V1 is 21 plus what's fractional for the remaining items. Now fractional for the remaining items with the remaining capacity, in fact, is going to be the same as this, right? So this is basically we are removing this item, and we have 16 left. And what can we fit in 16? We will take item 2 completely, item 3 with 5, and then 5 kilograms of item 4. And this will give us a value of 55. So this is going to be 76, which shouldn't be a surprise, right? In fact, we can, what's the observation that we can make at this point, and what's the generalization? Now, this is 76. It's not a coincidence that it's 76. We should have known that it's going to be 76 without doing these calculations. Why?
It's just the fractional knapsack for the whole problem?
Yes, why did it turn out to be the fractional for the whole problem? Because we, between the root node and this node, we have taken all items. We did not skip any item. Now, we will expect a difference at this node, for example, node 4. Now we will calculate the upper bound at node 4. Now we expect to see a difference because there is an untaken item. So untaken items are going to make a difference. So this is upper bound of 76. It's not a useful, well, yeah, so it's going to give us, upper bound 3 here equals 76. Okay, now at node n, so this is n1. At node n4, upper bound 3 equals the value of v1, because we have decided to take v1, plus fractional of what? Exactly, fractional of v3, v4, v5, and what's the remaining capacity? Still 16. So now we are solving a fractional knapsack for the remaining items, or the undecided items. And the undecided items at node 4 start with item 3. Item 2 is decided. We have already decided not to take it. Okay. Now let's solve the fractional for v3, v4. Let's do this fractional solution. So this fractional solution, we have 16. So we can take item 3, and it's gonna be 5 kilograms with a value of 15, and then we'll take item 4 with 10 kilograms. We can fit 10 kilograms because we have a remaining capacity of 16. So 10, and it will give us a value of 20. And then how much room do we have left? 1. We can take 1 more kilogram, and that's going to be 1 kilogram of item 5 with a value of 1. So now what value will this give us? It's going to give us 36. So now we will have 21 plus 36, and that's going to be 57. Now what's interesting here is that at node 4 we have upper bound 3 equals 57. Now upper bounds, the smaller the better, right? So smaller upper bounds are more useful because they will allow you to prune earlier, or they will allow you to prune less deeply in the tree at smaller depths in the tree. You know, the deeper you go in the tree, the more computation you do. So you would like the pruning to happen as early as possible, or at the shallow depths in the tree. You don't want it to happen deeply in the tree. Okay? So now this gives us 57, this gives us 64. So now what we are implying here, or the technique that as we are describing it, at each node, you take the value of, you look at the value of taken items, then you solve the subproblem of the remaining items with the remaining capacity. You solve it as a fractional knapsack problem, and you add the solution to the fractional for the remaining to the solution to the values that you have taken, and that will give you an upper bound. Okay. Now the question is, what's the running time at each node? How much computation will we be spending at each node in order to do this? Yeah. Yeah. So it's going to be O of n. In general, you know, when you get deeper, when you go deeper in the tree, it will be less than n, but it's basically the remaining depth, or the number of remaining items. So it's which is less than or equal to n, but we can say that it's O of n because earlier at the lower depths, it's going to be at the smaller depths, it's going to be n or close to n. So the computational time here for the fractional is O of n. So now we will be spending O of n time at each node. Now, comparing this with upper bound 1 can be computed in O of 1 time, right? This is O of n time. So why would we use an upper bound technique that takes O of n at each node? So do you think it will be a good idea to use this O of n? Why?
Because it is giving us a tighter upper bound.
Yeah, exactly.
Gives us
Yeah, exactly. So this is basically, the idea in branch and bound. You are willing to spend more time computing an upper bound if that gives you a tighter upper bound. But in general, you won't know if the overall effect or the overall result is going to be better or worse until you try it. You actually try it. So, analytically, you cannot. It's hard or near to impossible to prove that a certain pruning technique is going to give you better results, because usually to come up with a better pruning or lower upper bound computational technique, you need to do more computation at each node. More computation at the node, but it will give you more aggressive pruning, and more aggressive pruning meaning you prune an exponential number of nodes, the subtree. So usually we won't know until we try it experimentally and we see whether the results are better or worse. And this is something that you will actually try, and you will see that the fractional knapsack gives you good results. But in fact, there is a way of computing the fractional knapsack upper bound much faster. There is a way of avoiding the O of n computation. So even with the O of n computation, you will get good results. But there is a way of avoiding O of n at each node. Do you have any idea how we can avoid O of n and do something close to O of 1 at each node?
Type of hash.
What's that?
Hash.
But how would that help? How would the hash help here? So we don't have a search type of problem, right? So the hash would help us with search, but here it's not a searching problem. Okay, so the idea is to try to do the fractional knapsack incrementally, in an incremental way. So you start with this initial fractional knapsack when you haven't decided anything. Then when you make a decision, you modify the fractional knapsack solution. You modify it based on the decision that you have made. Now, if the decision that you have made is taking an item, will that modify the solution? No. When you decide to take an item, the your fractional knapsack solution remains the same. So here, we have decided to take this item and we got 76. Same as the solution that was at the root node. By the way, this is the initial solution. You can think of it as the upper bound at the root node. This is your upper bound at the root node. So upper bound here, upper bound 3 equals 76. And upper bound 3 here is 76 because we have decided to take an item. And in fact, I can tell you that upper bound 3 is going to be 76 as long as we are taking items. So we don't have to do any recalculation. Does everyone see this? That if we decide to take an item, because basically you haven't decided to untake anything, and the solution is going to be the same, except that now, at node 1, this will change from undecided to decided. It becomes decided, but you are subtracting its weight from the overall capacity. So basically, the remaining problem is going to be, taking the rest of the items. So the remaining problem is a subproblem of the original problem, as long as you are taking items. Now, when you don't take items, and this is the interesting part. Now, at node N4, now let's try to think how we can compute the solution incrementally, how we can get to this. Now, if we look at the original solution scanned the list of items in order of value per unit weight, and it stopped at item 4. Now, this is the solution. We stopped at item 4 and we took half of it, 5 kilograms instead of 10. Now here, when you take item 1, this is not going to change anything because item 1 is going to go away, and it's the weight of item 1 will get subtracted from the capacity. So the take decision is not going to change anything, but the untake decision, what will it change here?
Item 2.
Item 2 will not be taken. So now item 2 will go away. Now how will the new fractional knapsack solution change after deciding not to take item 2? So I will still take item 3, and now I'm in the middle of item 4. The idea is that I have 6 more kilograms that I can take. So I can pick up from where I left off. Pick up from the middle of item 4. I have taken half of item 4. Now I can add 6 kilograms to the knapsack by taking the remaining 5 kilograms of item 4 and 1 more kilogram of the next item. Okay? So in order with this decision of not taking item 2, all what I can say is at node 4, upper bound 3 equals the 76, the original upper bound, minus the value of item 2, which is 30, minus 30, plus what I can fit in the 6 kilograms that became available, the extra 6 kilograms that became available to me. And in the 6 kilograms, I can take 5 more kilograms of item 4 and 1 more kilogram of item 5. So plus value of 5 kilograms, or let's not complicate it. It's just going to be half the value of item 4, which is 10, and 1 of item 5. So this is another way of computing this. 76 minus 30, because this is the item that decided not to take, plus 10 plus 11, and this will give you the same 57. So if you just always keep a pointer, or just store the number of the the last item that you took a fraction of. Here it's item 4. It's the item that you could not fit completely, and you had to take only a fraction of. So this item, we call it the slack item. The slack item, it's the item that we took a fraction of. So the slack item was originally item 4. So here slack was 4. Here slack is still 4. But at node 4, what's the slack? Item 5, because now we took 4 completely, and we took a fraction of item 5. So at node 4, the slack became 5. The slack is the item that we take a fraction of. So we went further. By deciding to skip this, think of it as we skipped this, so we went further down the list of sorted items, and we took more of the remaining items, as much as we could fit in the extra weight or the extra capacity that became available to us. Okay. So now with this algorithm, now how much computation are we doing at each node? Can we say that it's O of 1? Can we say that we are doing worst case O of 1 at each node? No, we cannot. Why not?
Because couldn't you still be going through multiple items?
Exactly, yeah, because you can potentially go through multiple items. You will not necessarily go through a constant number of items. We cannot say that the number of items that you will go through at each node is constant. So we cannot say that the worst case running time at each node is O of 1. But what we can say is that if we do a sequence of calculations for a given path, if we go through a whole path from root to leaf, we will not do more than O of n items, O of n operations for a path. So do you see this? Now, if we do, because basically we are solving this fractional knapsack problem only once. So we start with a slack of 4. Here we change the slack to 5. When we decide not to take another item, the slack may change to 6 or 7. So we keep going down the list. So the running time for a whole path is O of n. So this is what we call the amortized time, or an aggregate analysis, where this is O of n for the sequence of n operations. So the average amortized time so it's O of n. The average amortized time is O of n divided by n, which is O of 1 per node. So it's not O of 1 worst case at each node. It's O of 1 amortized time on average. If you calculate n operations, it's going to be O of n. On average, each node will get O of 1, which means that intuitively, it means that if you go through many items at one node, that will save you computation at a later node. So because the number of items is limited, so if you go through 5 items or 6 items at one node, then at the later nodes you will go through fewer items. Okay, so doing more computation at one node will reduce the computation at later nodes. That's the idea. In fact, to show that it's O of n, the total time is O of n, we'll think of it. Okay, let me give a clearer argument that it's O of n for a whole path. A whole path where we start from a fractional knapsack and then we keep modifying it whenever we decide to untake an item. So a clear argument is the following. At each node, you will go through items, let's say, S plus 1, S plus 2, through S plus K. So in general, the items that you go through at each node is going to be S, which is the slack item. Then you can go through up to K, or in this case, K plus 1 items, right? Now, among these items, how many items in this list can be touched at other nodes? So if at a given node we go through S plus K, how many of these items can potentially be touched at other nodes? Well, no. Well, this is the slack, right? So if we made progress, we got past this slack, we went to S plus 1, the slack now will not get touched by the later node. It may have been touched by the previous node. So the S may have been touched by the previous node, but it cannot be touched by the next node if there is an S plus 1. And with S plus 1, S plus 2, S plus K, now S plus K is the only item that may get touched by the next node. So basically, S may be touched by the previous node. S plus K can be touched by the next node. What does it mean? It means that at any given node, there is a maximum of 2 items that will get touched at this node and other nodes. Because what may make this take longer than O of n is the fact that an item may get processed at multiple nodes. In fact, if you have a big slack item, that item may get touched by many nodes. Each node will make progress by a fraction of that slack item, right? So an item may get touched by multiple nodes. Now, what does this mean? It means that the items that get touched by multiple nodes, there is a maximum of 2 per node. And the items that can get touched by 1 node, right? We can't set a maximum or a limit on the number of items per node, but we can set a limit on the total number of items. So, do you see the idea? So there are 2 kinds of items. Items that may get touched by multiple nodes, which are at most 2, the first and last. So this is in general. Some nodes may touch only 1 item, right? And the items that get touched only by this node are going to be an arbitrary number of items. But we know that there is a limit on these because this is limited by the total number of items. The total number of items is limited by n. And while the number of nodes is limited by the number of nodes in a path is limited by n. So number of items touched or processed, let's say processed, for each node x, number of items touched by other nodes is less than or equal to. Now, number of items touched by only 1 node is the number of items that are touched by only 1 node. That's going to be less than or equal n. So these items that are by definition touched by only 1 node, there will be only a maximum of n because there is only n items, right? So this gives a bound of 3n. So we know that the number of items touched in a path is not going to exceed 3n. And this is a loose bound, in fact. So total number of items touched in a path is less than or equal 3n. And 3n is just, which is O of n. So this shows that you can touch O of n, a maximum of O of n items along any given path, which means that the average amortized time per node is O of 1.